Welcome back. Let's get ahead with a tutorial session where we will work on a Python notebook and take a little while to understand a little bit more about NetworkX. I've already given you a short overview using slides, but this is going to be far more useful where you can actually look at the exact commands that we use to build graphs of various types, visualize them and so on using NetworkX. So, this is a quick introduction to NetworkX where we will first look at importing network data as a NetworkX graph object and look at how nodes look like, how edges look like, how they can be accessed, manipulated and try to see how we can draw them and customize the visualization in terms of the size and so on. So, first we need to import all the necessary packages and these are the classic Python packages that we always need. So, first import numpy, pandas, matplotlib.pyplot. So, this is for plotting and matplotlib itself as well, then NetworkX. So, once we have these, let us see how we can read various kinds of files, because as we discussed in the class, there are various ways in which you can store a graph, right. You can use an adjacency matrix, an adjacency list, an adjacency map and so on. But we did see that the simplest, even if a little inefficient, the most simplest and widely usable way to store networks is an edge list. So, how do you store networks as an edge list? We just put in all the edges. So, let me just quickly show the file how it looks like. So, let me just first show you how these text files look by opening them. So, here it is. I am just going to quickly open them in Sublime Text. So, this is an adjacency list, this is an adjacency matrix and this is an edge list. So, this is an adjacency list, here is an adjacency matrix and here is of course the edge list that we wanted to look at. So, there are, you can see 8 nodes and 14 edges, right. So, there is one line per edge. So, now let us look at loading it. So, very simple, G equals nx.read edge list from the file direct, right, and you can say it has to be created using either nx.graph or nx.digraph, whether you want it to be an undirected graph or a directed graph. So, let us run these. Let me first run this. Now, pandas is also imported. There you go. And now, I am going to read this graph, okay, and that is this. You get the same output. So, let us just there you go, these are the nodes. And we already saw the edges, okay. And you can also create a directed graph. So, when I do this, it creates a directed graph. Well, let us just run that. There you go. And I can also do the same thing from an adjacency list. And I get the same output and I can also make it into a directed graph. I get the same output that was there in the file originally. But more interesting, I can also build it from a pandas data frame directly. So, here it is, I am loading it into edge list, loading the edge list into a data frame and I basically get the same set of edges, right, and I can also do it as a directed graph. So, this is very important. I mean, it is the simplest set of commands that you will use, but this sets you up for working with any kind of complex network in NetworkX and Python. So, you load it either into a pandas data frame or you load it into the adjacency list directly or from an adjacency matrix and so on. So, there are various things. We are currently only looking at the edge list. Let us move ahead. Here you go, where we can use an adjacency matrix. So, you read CSV using pandas, and you basically use the delimiter as a tab because that's what's used in the file and not commas, and here you go. Okay, and you can directly create it as a graph, or you can use a digraph and so on, and you can also export it. I want you to look at this a little bit more closely. You can just write it to an edge list or an adjacency list or a pandas edge list or and so forth. So all of these exports are possible. So this way, the first thing that you have to figure out when you work in a new topic or in a new package is how do you do all these interchanges? How do you interchange between a few formats? Because that becomes very essential for us to understand. That becomes very essential for us to work with these kinds of networks. And so there will be networks available in various formats online. There are websites like Network Repository or any other data source. So you may have to crunch it and build your own network. But when you build your own network, how do you manipulate it? How do you switch it between multiple formats and so on? So all of those things are readily possible with NetworkX with these simple commands that we just overview. And it turns out that there are a ton of other data types that are supported. It can use a NumPy array, a dictionary of dictionaries, a multi-line adjacency list, and so many other interesting formats. You can read a little bit more about them, especially when you suppose you find a paper that's presenting something in a GraphML format. You know how to, where to look for information. You can consult the NetworkX documentation, and you can basically load GraphML, JSON, LEDA, Pajek. These are all famous. Some of these are famous software tools to work with networks. So how do you look at, now let's look at the nodes and so on in the NetworkX graph object. So you've created a NetworkX graph, and let's say we add a node, and you can add a string, float, or even like functions and all kinds of things. So let's just go and do this. So you have a graph. You have a graph with 4 nodes, and this will give you the node view that we saw a little while ago. Okay, you have different types of nodes, and here I can also add various kinds of attributes. So again, I'm creating a graph, adding nodes of different types, and now you look at the node that is identified by the string, right? So let's just look at nodes again, and so this is the node identified by 1, and this is the node identified by 1.2, and this is basically a dictionary that gives any information, right? So let's just try to let's just try to add a few more properties maybe. I just made something arbitrary. We'll see what this is later on in a moment. So g dot nodes, okay, and now I've given it an arbitrary attribute called size, and I've assigned it to 10, an integer. So I can just put any string there. So whatever string I define will go into a dictionary which is corresponding to that particular node. So you can see this is highly flexible and very quickly and quite powerful as well, and very quickly you can do all kinds of operations on this and initialize a complex graph and things like that. Here you go. Here I can add edges and edge weights, right? So here I go. So let's just okay. So these are the edges. These are tuples essentially. Okay, it's a typo. These are the so this is every tuple of this sort is an edge, and if you put an edge that doesn't exist, you get an error, right? So because this edge does not exist. And so you have different kinds of graphs in NetworkX. The standard graph is a graph with an undirected graph with self loops. So all graphs can admit self loops. And then you have a digraph, which is a directed graph. Then you have multigraph, which is an undirected graph with self loops and parallel edges, meaning you can have a pair of edges between the same pair of nodes. Each of these could have a different weight or whatever, like, think of multiple flights between the same pair of cities, right? So you may still want to model them as a network where the nodes are cities and so on, and you will have multiple edges connecting these cities. And you can also have a multi-digraph where you can have a directed graph with self loops and multiple or parallel edges. So here you go. So edge list is 1 2 1 1 2 1 3 2 3 3 3 and 3 2, right? And so if you look at this, when I create different edges, different kinds of graphs, undirected graph, the edges are just 1 2 1 1 2 3 and 3 3, and because it subsumes, right? So you have 2 3 and 3 2, they are subsumed here. So this is the undirected graph that you get. So whereas in a directed graph, all the 5 edges actually happen. For a multi-undirected graph, you have 2 of these, 1 2 1 2 remains, and you also have 2 3 2 3, because 2 3 and 3 2 are quashed as 2 3 2 3. And then for a multi-directed graph, you have the exact list here, 1 2 1 2 1 1 2 3 3 3 and 3 2. So you can clearly see the distinction between these different kinds of graphs and how they can be readily used how you can use NetworkX to readily build these kinds of graph objects, which you can then process using a variety of algorithms. You can run various algorithms on it, various centrality measures, study the degree distribution, or any other kind of properties you want to examine in these graphs. And now let's look at drawing graphs. So NetworkX has various kinds of graph layouts, so including planar, circular, spectral, spring, and some classic algorithms which use different kinds of logics to make sure the graph looks less cluttered. There are various number of edges from each node, okay? So you can get a really complex and potentially cramped and cluttered network where you have too many edges and intersecting and things like which intersect and so on. So what you want to do is you want to lay them out in such a way that visually the network has not too many not too many edge intersections, and the nodes are far apart appropriately and things like that. So let's just try to build some of these. So this is a simple graph. Let's just see how it looks in different layouts. So I'm going to see if this works using matplotlib. So again, SciPy is missing here. I thought we imported it, but Okay, so now this should work. Let's just try it again. Yeah. So you have a blank plot here because of subplot, you can ignore that. But then here is a planar graph, here is a circular graph where the nodes are laid out somewhat circularly. Then there is a spectral graph layout, spring layout, shell layout, and so on. So each of these layouts has a different logic, and for every single graph you may have different, these would look different, and obviously, and you may want to figure out what is the best way to lay out your graph of interest. It really depends upon your degree distribution, density, and all of those. And now how do we alter the color of the edges, right? Or how do we alter the thickness of the edges and the color of the nodes and so on. So here's a simple graph. Yeah. And you see this? So you have, let's just change it to say yellow. It's cleaner. Yeah. So here you go, 1, 2, and 3. So I can actually use different edge weights. So let me change the edge weights. So you saw this became much thicker, and so you can really alter the node sizes. Let's see. Yeah. You can alter the node sizes any which way. So you can use the sizes that you define in the graph as well. You can just map a property. You can just, this is just an array, right? So you can even fetch it from the node properties or attributes and so on.